Last class, we have seen about the Schrödinger picture and Heisenberg picture and their significance. In this class, we will see in detail about the interaction picture. Uh, it is also called the Dirac picture, which is very much useful in solving the perturbation problem. So we will see in detail about the Dirac picture. Last class we have seen about the Schrödinger picture and Heisenberg picture. In this class, as I said, we are going to see the Dirac picture. Uh, we will, before going into the detail, we will see the major difference between these pictures. As we have seen in Schrödinger picture, the operators stay fixed, while the quantum state or state vector changes with the time. In contrast, in Heisenberg picture, the operator depends on time, while the quantum state, that is a state vector, is fixed. In Dirac picture, uh, both the operator and quantum state depends on time. As I said, in interaction picture, both operators and quantum state, that is a state vector, carry the time dependence. So the Hamiltonian, which depends on time, can be separated into two parts. One is H naught, or the other one is H prime, which depends on time. This is independent from time, it is solvable, so easily solvable one. And one more important point, you must note that the wave function in the interaction picture, we know that in interaction picture, both Hamiltonian and wave function depends on time, which depends on time. Uh, is defined as the exponential term. You can see this is actually U dagger. That is a complex conjugate of time evolution operator, not the time evolution operator. And moreover, you uh, must note that in earlier two picture, we used H. Here we have used H naught. That is the major difference. That is which is solvable. So e power I H naught. I want to stress this point. This is not H. It is H naught T over H cross. Uh, we have taken the Schrödinger wave function because Schrödinger wave function depends on time, not Heisenberg. So we have taken. In fact, Dirac has formulated like this. Dirac has taken this Schrödinger wave function for his interaction picture. This picture is very useful to solve the perturbation theory. It is useful in perturbation theory. See here, you can notice one beauty that this time dependent Schrödinger equation can be taken as zero. Will be taken as zero if the time evolution operator act on this Schrödinger wave. So here time evolution operator is e power minus I h naught t over h cross. So when this term, this time evolution operator act on the wave function psi s, it will be psi s of t. So you know the value of this one, this exponent u dagger is a unitary operator. U dagger is equal to 1. That is the interaction wave function in interaction picture or state vector in interaction picture is equal to the wave vector in the Schrödinger equation when time t equal to 0. Earlier we have seen that when t equal to 0, Heisenberg picture and Schrödinger pictures are the same. Likewise, all three fixtures are same when time t equal to 0. Now we will come to the original problem. By definition, the operator in interaction fixer is equal to the operator in Schrodinger fixer, because in Schrodinger fixer the operator is time independent, so that you have to take care. So u dagger a u is the ai. When h prime is equal to 0, then naturally h naught, which is time independent, operator is time independent. So it will become starting a picture and interaction picture are the same. So we have seen that get psi I, which is a function of t, is equal to by definition e power I h naught t over h cross get psi s of t. Now we can write this as psi s of t is equal to, when you bring this exponential term to the other side, you will get e power minus I h naught t over h cross. Uh, with this get psi I t. Now you differentiate this one. If you differentiate in the right hand side, the exponential term, first you differentiate the exponential term, this will become I over h cross, which can be written as minus 1 over I h cross, and this exponential term comes as it is, and this h naught comes to the get vector. So then you differentiate the, next you keep the exponential term as it is and differentiate the get vector. So we know the standard differentiation from Schrodinger equation I h cross t psi by dt equal to I h times psi. So r t psi by dt, you bring this I h cross to the other side, you will get 1 over I h cross h psi. So now you replace this here. So 1 over I h cross h psi s Schrodinger fixture psi s of t. So I have replaced this. Now you see I want to bring all in terms of the way that is the state vector in terms of the interaction fixtures, that is psi sub I. So here you take psi s of t, and here one psi s of t state vector, which can be replaced by this one e power minus I h naught t over h cross get psi I t. So I have done that. So here you note that h naught, here h, this is u dagger, this is u. Similarly, this is u dagger, this is u. That also you have to remember. We will see what will happen to this. So we have seen this expression. You can see in the first term and the second term of the right hand side contain 1 over I h cross. So you bring 1 over I h cross to the right hand side, sorry, left hand side, it will become I h cross. So remaining term you can see. You can see carefully here you have minus e power I h naught t over h cross h naught e power minus that is inverse of this one, minus I h naught t over h cross. Same thing is here. So you bring h naught, this get vector also same. That is get psi I of t is same. So I have taken that as a common. And this also, this exponential term also common both cases. So here exponential I h naught t over h cross and inverse. Here also same thing. So I can take this as a h. H is plus minus h naught. I am taking remaining thing as common. What is h minus h naught? By definition, h is equal to h naught plus h prime. So then h minus, if you bring this h naught here, h minus h naught is equal to h prime. That's what. So I have written this h minus h naught as h prime. So finally I have arrived with this expression. So now we got this expression. Here you can see that this exponent term and the inverse of this exponent term. In between you have h prime, which is defined as, this is defined as h I prime. I indicate the interaction picture, which is a function of t time t, which act on the get vector psi I, which is a function of t. This is the Schrodinger equation in interaction picture. You can see this is analogous to I h cross t psi by dt is equal to uh, h psi. Here instead of h you have h I prime, and this is the time evolution. That is time evolution of the state psi I. From left hand side you can visualize that. So this is the Schrodinger equation in the interaction picture. It shows that the time evolution of the state vector is governed by interaction. That is, that interaction term is this Hamiltonian hi prime t, which depends on t. This picture is very much useful to to solve the problem in perturbation theory, and it is mainly used in perturbation theory. Now we will see the time derivative of the operator in interaction picture, that is trap picture. So if you differentiate and rearrange the term, I have done same thing in the case of Heisenberg picture. So you will get 1 over I h cross that operator. Here instead of h you will get h naught, because here in the exponent term you have h naught, not h. So other than that, it is similar to the Heisenberg equation of motion. Here AI, this is interactive operator, so which depends on time. If A is explicitly depends on the time, then you will get this extra time as usual. I have explained about the extra term in the case of Heisenberg pictures. This Thank you very much for watching my video and supporting me continuously. Thank you very much.